Hello, and welcome to this Flexible Circuit Technologies webinar. My name is Matthew, and I will be your Global Spec moderator. Now let me introduce today's presenters. With us today, we have Mark Finstead, the Director of Application Engineering for Flexible Circuit Technologies. And we also have Carrie Burkett, the Vice President of Flexible Circuit Technologies. To read more about our presenters, please look at the speaker bio window right next to the main presentation window. And guys, welcome to today's event. And with that, I will pass things along to you to get started.
All right, thank you, Matthew. This is Carrie Burkett, as Matt said, FCT Vice President. I'm just going to do a brief introduction and then we'll get into the content. One of the things we've done is we're going to switch up and go with electrical, mechanical requirements first, just because it's a lot more content, and if we have time, we will get to cost drivers. The electrical, mechanical conflicts that come up, we deal with all the time, and like I say, can't we all just get along? So that will be what we cover. As a brief introduction, and this is just kind of an advertisement, FCT, we are a premier global supplier, flexible circuits, rigid flex, flex heaters. We do EMS assembly all the way to product module and complete product box builds. We're headquartered in Minneapolis, and most of our production facilities are in China. Shenzhen's our main hub in China. And just at the highest level, again, flexible circuits, single, double, multi-layer, flex, rigid flex, HDI, large format circuits, membrane switch, plastic components. We have an EMS assembly facility, do a significant amount of assembly. From there, break down, do a lot of business, medical, consumer, automotive, industrial, telecom are the main markets that we serve. Our factories in China have 16949 for automotive, 13485. So we do have robust quality systems in place. Further within the medical market, we also do FDA registered product box builds as well. This just gives you pictures of the different facilities we have. Probably the biggest thing I would point out is that the flex, rigid flex, flex heaters, this market continues to grow rapidly, and one of the questions we like to ask is who's designing your circuit, because the fact is it's growing so fast that there's just not a lot of true expertise with people that have, long-term experience in where they understand the materials, material properties, what can and can't be done, how to get to a design that can be produced at high yields, all aimed at saving costs. And that's really where we shine. You can go to our website and find backgrounds of our key people, but all of our senior application engineers here have 25 all the way up to 40 years and focus on flexible circuits, rigid flex, on design and fab. So we bring a ton of expertise that, again, helps our customers save dollars. We have our capabilities chart, again, that's available online. We do membrane switches, flexible heaters. We have a plastic molding group as well. We make products for medical companies. We have EO sterilization. We also opened up a year ago our brand new Zhuhai facility, which is a flex, rigid flex, flex heater production facility. We're in the process of building a brand new EMS facility in Huzhou, China. Today we do our assembly in Shenzhen. We have a ton of expertise in the assembly area as well. And that's really all I'm going to point out. I think the key here is here's our contact information for Mark and I. And if you do have interest in finding out more about our company after the webinar or want to contact us, you can take this information and certainly follow up with us, and we'll be happy to provide more information on flexible circuits. But with that, I'm going to let Mark jump in. As Matt said, Director of Application Engineering for us, 40-plus years. You can read his bio, and we'll get on with the mechanical and electrical requirements presentation. Thank you.
Okay, thanks for joining. And if you have questions, we will have a Q&A at the end, but if you have questions, before that, by all means, send them in. I'd much rather address what's interesting to you than what I have in my slides here, so you can throw them in, and if it's something I'm going to cover later, I'll let you know. Otherwise, we'll address them as they come in. So anyway, today we're going to talk about decisions that are made by the designer when you're putting together a flexible circuit. And you have a lot of things you have to weigh, and unfortunately there's a lot of conflicts when you're doing a design. Flex circuits are unique in that, unlike rigid PCBs, for a rigid PCB you typically have to make sure that all the connections are there and that you have your signal integrity issues taken care of, and basically just electrical stuff, and as long as all the dots are connected, you're good to go. Flex circuits have all of the same types of requirements electrically, but in addition to that, most customers want to be able to bend and fold them and do all kinds of other things to them to really get the use out of the flex circuit. And unfortunately, a lot of the things that you do to improve one aspect of your flex, either mechanically or electrically, typically is detrimental to the performance of the other features. So we're going to go through some of those and just show the examples of what can happen as you're moving through your design. So if you look at the typical electrical considerations, these are similar to what you would see on a rigid PCB. You have your current requirements, current carrying capacity, you want to keep low conductor resistance, your voltage requirements, signal integrity. I'll address each of these one at a time. So if you look at your current requirements, anytime you have more than a couple hundred milliamps, you have to look at the trace that's going to be carrying that current. There's enough other things in your system typically that are producing heat, and so you don't want the flex circuit to be a heater in and of itself. So you're looking to keep your resistance in your traces to a minimum, and that will reduce the amount of temperature rise that you have. And this is a snapshot from IPC 2152 that shows how you can get more temperature or less temperature in your traces based on the size, the thickness, and the width of the circuits. So typically, there's really only two things that you have as tools to reduce your resistance in your traces, and that's your conductor width and your conductor thickness, basically the cross-sectional area, unless someone's come up with a way of making a cost-effective solid silver PCB or a superconductor that'll run at room temperature. These are really the only choices we have with copper, are either thicker or wider. And both of those can work against you when it comes to flexibility. If you have thicker traces or wider traces, they're going to take up more space on your layout. And if you are using up all of your space on a particular layer, it may drive you to additional layers. And additional layers equals additional thickness and makes your overall thickness more and makes the stiffness a lot higher. If you have an increased copper thickness, if you use a higher weight copper for your traces, you also have to increase the thickness of your adhesive to be able to fill between those conductors. And so that's an additional whammy that you have going. So you end up with an overall thicker and stiffer circuit. An example, this would be a cross-section of just a standard two-layer flex that doesn't have any impedance or current requirements. And if we just use our standard materials, we're looking at about 0.06 of an inch overall thickness for a two-layer part. Now, if you throw in, say, 2 or 3 amps of current on some of those traces, now we have to go with 2-ounce copper in order to carry that current. In addition to the 2-ounce copper, you're also going to have 2-mil adhesive to be able to encapsulate all the traces. So when it's all said and done, you look at the difference, you can see that you've over doubled the thickness of the circuit just because you had higher current traces on one of the layers. So it's important to look at how that's going to affect, and like I said, it's going to be a lot stiffer when you have the high current traces. So again, you're going to have to get the higher current, you're either going to have wider traces or thicker conductors. It's going to make the circuit overall stiffer if you have high current, and the extra adhesives are going to be working against you. And so typically what we see is if you have high current in your application, you're not seeing those used in dynamic applications. They just aren't going to be able to flex continuously because of the extra thickness. And so those are typically only going to be used in static applications. Another requirement is your voltage. If you're only using low voltage requirements, you don't have these issues. But if you do have higher voltage issues, you do have to take that into account. Your higher resistance, insulation resistance, and also your dielectric breakdown strength. The good thing is flex circuit materials are really superior to anything in the rigid board industry for dielectric breakdown. The polyimide films are good to almost 5,000 volts per mil of thickness. The thermosetting adhesives are over 2,000 volts per mil of thickness. So you have really, really pretty good voltage characteristics and isolation characteristics on your insulators. But if you do have high current or high voltage rather, you do have to take that into account. The way you would take care of that is either spread your conductors out so they're not too close together. If you've got 5,000 volts of potential between two traces, the only thing between those two traces is going to be adhesive. And at 2,000 volts per mil, you're going to need to have enough to be able to maintain your isolation and have a little bit of a safety margin also. So as you space your conductors out, you're going to increase your the amount of real estate you're using. Layer to layer, you're going to also have to space that out. With polyimide, typically if you're 1 mil or thicker with your polyimide layers, you probably don't have to worry about that too much. It's only if you have 0.5 mil or less for your polyimide layers. We typically don't see any issues with 1 mil or thicker as far as layer to layer. I can say that in 40 years, I've never seen a layer to layer dielectric breakdown in a flex circuit because of the polyimide. But I have seen them occasionally. It's rare, but you see them occasionally with 0.5 mil polyimide. So if you do have high voltage, you're probably going to want 1 mil or thicker for your layer to layer separation. So if you have if you've spread your traces out and you've used additional thickness on your laminates, you can tell that you're going to, you could be increasing the number of layers that you have if you've used up too much space because you had to spread your traces out. Obviously, if you're using thicker core material, that's going to make it thicker. And so overall, it's going to get a lot thicker, and that extra thickness is going to make it more stiff. Signal integrity is a really big issue. More and more now with everything running at high speed, we're seeing it in just about every application. You're looking about impedance control, crosstalk, insertion loss is a huge deal. The signals just are not, they're so small you just cannot afford to have any lost in the transmission line. Also isolation, you want to make sure that your signals are not transmitting and or receiving noise that you don't want on your on those traces. Typically, when you do have signal integrity issues, it goes with impedance control, and that's usually a reduced trace width. You have to increase your dielectric spacing between your signal and plane layers. I don't have a specific slide stating this, but one thing about impedance control is you will always have at least one plane layer and typically 2 plane layers, and those will have a huge impact because you're adding 2 additional layers that wouldn't be there if you did not have impedance control. So it's important to keep in mind that that's going to have a big impact, especially if you're using copper for those planes. And I'm going to address that a little bit further in here. You can use non-standard low dielectric constant and low loss materials, and until very, very recently, those materials were limited to some very, very difficult materials to process. They were thermoplastics like LCP or Teflon, and they processed at very, very high temperatures. Typically, you had to laminate them over 300 C, which put it out of the reach of most flex circuit manufacturers just because the equipment typically doesn't go up to those temperatures for standard materials, and so you really limited your vendor base. More recently, they have introduced some low loss materials that do process at more standard temperatures, They are more expensive, but it does give us a another option to be able to get some of the requirements that we need without making them a lot thicker and not go into a really strange material. If you do have, if you are using an exotic material, like I said, almost even the ones that are processing at normal temperatures are more expensive. The LCPs and some of the other high temp ones were also very expensive, so that's going to have a big impact on your cost. You will have lower yields because the thermoplastics are much more difficult to laminate, and you're going to have fewer suppliers. And anytime you have fewer people doing a particular product, you're going to pay a premium for that. So this is an example of a very flexible type 2 circuit that doesn't have any current or impedance requirements. Now, if we added in a 50 ohm impedance requirement and went with a microstrip construction, which is just a single plane layer, you can see that you increase the overall thickness by almost 50%. And that's just with a single plane. That will give you the impedance that you need, but it's not going to give you the same isolation as a strip line construction would give you, and that's with 2 planes on the outer layers. If we had to go to a strip line construction and we use the same 50 ohm requirement or 100 ohm requirement, we're looking at almost 2.5 times the thickness of the previous one. So I mean, it's a huge difference. And I'll scroll back again so you can see you're going from no requirement to a single 50 ohm strip line up to 100 ohm differential with planes on both sides in the strip line. So it's going to make it a lot thicker. And you can see you went from 6 mils in one up to 20 mils, even though electrically they're going to be very similar, but in high speed you will have, you'll get the performance you need, but you're also going to have a much stiffer and thicker circuit. So when you are doing high impedance, or typically elevated impedance, because the standard flex circuit, when you don't take anything into account, is going to be a much lower impedance value than most systems need. So once you start elevating, trying to get up to 50 ohm, strip single-ended or 100 ohm strip line or 100 ohm differential, you're almost always going to have to add additional dielectric thicknesses to spread your signal traces from your planes. Those added shield layers are going to increase your thickness because you're adding additional layers. The planes are typically solid copper, and so that's going to add more stiffness. One thing to consider is to use a strip or a crosshatch pattern for your planes. And what I mean by that is to basically take out a dot pattern or a diamond pattern or something in your plane layers, and that will allow you to get a little bit more flexibility. And the other advantage is by removing a portion of that return path, you're elevating the impedance without spreading the conductors or the planes out and separating them from the internal layers. And so this allows you to get elevated impedance without increasing the thickness significantly. And most of the impedance calculators nowadays will have this as an option to go in and put in a crosshatch plane pattern and give you the impedance that you're going to get. One thing to keep in mind is if you have solid planes in certain areas and crosshatch planes in other areas, when your transmission line transitions from crosshatch to solid, you are going to have to change the line width to keep your impedance matched all the way through. Also, if you're going to use a crosshatch pattern, you typically want to run your crosshatching 45 degrees to the length of most of your transmission lines. If you were to turn it so that it was parallel or orthogonal to your transmission lines, there's a chance you could have some of those traces that are going to be coupled to a parallel line in your crosshatch and have a different impedance than the one next to it that could be just hitting the cross pieces. So by turning it 45 degrees, you end up with a more even distribution of coupling from those planes to the traces below. And another thing to consider to try and get it more flexible if you do need impedance or isolation is a shielding film. And there's a couple different versions on the market these days. The most common is made by Tatsuda, and it's basically a single laminate that has multiple layers in it that have an anisotropic adhesive and a conductive layer and also an insulating layer. And the entire stack-up is less than a mil thick, and so you can add that to your outer layers. You put holes in your outer covers in your flex that expose traces that you want to connect your shield to below, and so the anisotropic adhesive will make those connections. And you can end up with a much thinner circuit and still get some of the benefits of a full copper shield. So if you look at this picture right here, this is a cross-section of a multi-layer circuit that has a single layer of copper and two planes, and those are assuming that you're using copper planes. You can see the overall thickness. Now, if we were to eliminate those two outer copper planes and put in the shielding film, this is what it would look like, and this is pretty much to scale. And so you can see that you're significantly reducing the overall thickness of the circuit. So that's going to give you a lot better flexibility and still give you a good isolation and impedance requirements that you can meet. So if you select materials with a lower dielectric constant, you can have they're typically more expensive, and you do have a limited supplier base for those materials. So another thing to think about when you're designing your flex circuit are some of the physical and mechanical considerations, your operating environment, looking at your ambient temperature, physical space limitations, and your chemical resistance, and the application, whether it's static, dynamic, shock and vibration, combinations of any of the above. And all those have to be taken into account because, like I said, the flex circuits are usually crammed in. They're on multiple planes when they're installed, and so all of these things have to be evaluated when you're doing your design. If you look at operating temperature, flex circuits are, for the most part, all made with thermosetting adhesives bonding everything together. It's a film adhesive that comes in a B stage as a raw material. And when the manufacturers laminate them together, they cure and stay flexible when they're cured. The problem with thermosetting adhesives is they do get fragile when they're heated up, and it doesn't take a whole lot of heat for them to start getting fragile. They can handle, a flexor can handle a 550-degree solder float for 10 seconds pretty easily, and that's usually just a static exposure to the heat. And for the most part, they can run at well over 100 C continuously without any problems if it's static. However, if it's something where there's a lot of shock and vibration and it's seeing those elevated temperatures, you can start doing damage to the circuit because it will get much softer. And I've actually seen examples in the past where heavy components have been added to a flex circuit, and they've gone into an oven for a cure of some sort, and an operator pulls the flex circuit out by the flex itself, and as soon as those heavier pieces drop out of the oven, that shock can actually rip the flex circuit because it's gotten so soft during the baking cycle. So if you have thermosetting adhesives, like I said, which encompasses virtually everything out there, you have to be careful on what you're going to be running at for your ambient temperatures. You can use some high temperature adhesives, but this really limits your vendor base because, again, these all laminate over 300 C, and there's not a lot of flex manufacturers that have equipment that can laminate at those temperatures. It will make a stiffer circuit also because they're not as flexible as the thermosetting adhesives, and they'll be considerably more expensive. You also have to look at your physical space requirements, tight bend radius, your circuit size and thickness. All the things we talked about earlier that are making your circuit thicker are going to work against you when you try and form this. And we could go in and spend a couple of hours just on what you can do to a flex circuit when it comes to bending and forming it. But it is important to keep in mind that anything you do to make it thicker is going to make it tougher to install. Chemical resistance, if you have requirements where polyimide for the most part is pretty darn resistant to most chemicals. It does seem to, its weak spot seems to be alkaline solutions if they're a very strong alkali. And from a saltwater perspective, they're not great for long-term salt exposure. Typically, if you have those types of things or other chemicals that do attack polyimide, you're going to have to put on a cover like a Teflon or LCP over the top of your existing cover. And again, those are difficult to work with. The Teflon, well, there's a reason they coat pans with it because nothing sticks to it. So it's difficult to use that as a cover material and make it stick. It can be done, but it does require a special grade of Teflon and some special handling and processing to be able to successfully bond Teflon. And LCP is kind of in that same ballpark, very difficult to work with and very expensive. It'll also add additional thickness if you have to add those layers over the top of your circuit. So chemical resistance can add additional mechanical issues that could cause problems when you're trying to install it. Your application as far as static or dynamic, I talked a little bit about your high current applications, and those are typically only static. The vast majority of flex in general is static applications. Dynamic, we don't see quite as many of them. They are out there. Dynamic is a kind of an animal all by itself that requires a lot of additional requirements in order for it to be able to handle, you know, hundreds of thousands or millions of cycles. For shock and vibration, flex is actually fantastic for shock and vibration. I've personally designed interconnects, flex interconnects that see over 20,000 Gs during their one-time use. You can read whatever you want into that. And they typically perform very, very well because the mass is so low on flex. They actually do really, really well for both shock and vibration.
We did have a question come in if you want to take that, Matt.
Yeah, guys. Hi, this is Matt. We did have a question that came in from the audience. So to the audience member that sent that in, thank you. And to the rest of the audience, you can submit a question at any time. We will be answering throughout, and we'll also have a Q&A session at the end. But for now, here's the question. Is there a way to calculate the minimum bend radius for strip lines, especially for strips that have very thick parallel copper layers?
Good question. And this isn't just for strip line, it's basically any flex. It's basically a bend ratio. And if it's a strip line, it's going to be at least 3 layers, which makes it a multi-layer. And the IPC recommendations are 20-to-1 bend ratio. It means 20 times the circuit thickness for your minimum bend radius. And that's assuming, again, a static bend, where it's a single one-time bend and it's not dynamic. If it's dynamic, then you're going to have a pretty in-depth discussion with some designers and a manufacturer to figure out how to do that, because that's going to be a tough go. I would say that if you needed a dynamic application, you're almost going to have to go with a shielding film in order to get it thin enough to be able to operate dynamically long-term. But for static application, figure 20-to-1 circuit thickness to bend ratios. And you talked about having thicker traces, so that probably would be a good guideline. And that can be violated within reason. Typically, the guidelines in IPC are a little bit conservative so that you know if you're safe or if you're in a danger zone. If you drop below that, it doesn't mean it can't be done. It just means that you probably should have some discussions with your manufacturer to find out if there's a problem. You may need some specialized forming tooling to assist in having it formed. If you have a very large bend radius, a lot of flex are just formed by hand, and that's fine if you have a 150-to-1 or 200-to-1 bend ratio. If you're trying to get down to a 20-to-1 or a 10-to-1 bend ratio, it's better to have some type of a tool so that everybody gets the same results. You don't have, an 80-pound woman doing it on first shift and a 300-pound linebacker doing it on second shift and getting completely different results. So it's important to take that into account in your designs. So thanks for that question. So anyway, just to conclude, when you're designing your flex circuits, it really comes down to a balancing act. And too many times, a design is driven too much by one particular feature, electrical features, for instance, and you can have a circuit that is absolutely flawless electrically, where you have the most pure signals going through it, but if you form and put it in your device and it breaks in half, it doesn't really do you any good. So you have to have a balancing act, and usually it's something where it's a little bit of give and take, where you may not get the 100 ohm impedance that you wanted, but maybe 90 is good enough, because that will allow you then to be able to bend it and actually get it to function mechanically also. And so that's where it's important to kind of weigh everything out, and then also look at some of the tricks that are out there, using crosshatch shields, using shielding films, for instance, and anything you could do to try and be able to get the best of both worlds. But it is important that, when you're designing, you're looking at all of the aspects that flex circuit is going to be exposed to, both electrical, mechanical, physical, chemical, everything, to make sure that they're all covered at the front end, because it's awfully expensive to find those mistakes after it's in the final device.
We also had another question come in, Matt.
That's correct. Yes, we have another question. Thank you to the audience member that sent that in. And here's the question. What value is considered high current?
High current, I would say when you start getting over about 500 milliamps. Most applications are signal current, where you're only looking at, under 100 milliamps. Anytime that it's, half an amp or more, that's getting to be pretty high. And the other issue with high current, in addition to just the fact your traces get hot, they're noisier too. If you have a high current trace sitting right next to a signal trace, you're going to have a lot of noise on that, especially if it's AC current. So it's important to take that into account and get some separation between those high current traces. If you're just looking at milliamps, typically those are low current, and they can sit right next to each other and they play nice. But if you have higher current, anything over, like I said, about half an amp, you have to start looking at where that is in relation to your quiet traces to make sure you're not talking to them.
I think, I know that concludes this portion. We have the cost drivers, and we have probably 10 to 15 minutes. Is that good to go through those?
Yeah, we'll get into cost drivers.
Yeah, let's jump into cost drivers.
Hopefully this isn't my audience right now. So when it comes to the prices of flex circuits are always going to cost more than a comparable rigid PCB, and that's 100% of the time. If all things are equal, same layer count, same feature size, same size and shape, the flex circuit's always going to be more expensive, and it can be a lot more expensive. Sometimes it's only 3 or 4x, sometimes it's 50x. It can be all over the map, and there's a lot of things that drive that. Mainly, it's because of the thin materials that we're using. And the thin materials bring in a lot of complications that rigid board manufacturers don't have. The materials themselves are much more expensive. FR4 is very, very cheap. A lot of the materials that we buy, we can spend, $15, $20, $25 per square foot just for the raw material per layer. So if you've got, an 8-layer flex and you've got 4 base laminate cores and you're paying $25 a square foot for them, you can see how much money you've got per square foot just in raw materials before you actually start processing them. So that's one of the things. Probably a bigger thing up and beyond just the raw material cost, though, is that they're fragile. They're so easy to damage. If you take a large sheet of material and you pick it up off the table from a corner, you can damage it just because you can get a ripple that'll run across the copper, and it's almost impossible to to get that area to not etch out when you're doing your photo etch process. So that's a concern, and it's also dimensionally unstable. And I'll go through some of the problems with that here later in this presentation. So when you look at the heavy hitters on a flex circuit costing, some of them are the same as you'd get in a rigid board. Your layer count, your circuit size, your circuit shape, your pallet requirements, and the circuit size and shape can have a huge impact on the cost. Here's an example of let's say this is a standard 12 by 24 processing panel, and flex circuits are for the most part all built in panel form. There's some roll-to-roll processing, but only in really, very, very high volume applications where you're doing millions of parts. For anything under that, you're typically running them in panel forms, and those panels are different. They vary by manufacturer. But let's say it's a 12 by 24 panel, and you put a circuit on that's just slightly over the halfway point. No matter how I panelize this, the best I'm going to do is get 4 parts on the panel. So your cost for this part is going to be my panel cost divided by 4, roughly. Now, on a part that big, the question is, did it really need to be that long, or could it be shrunk up just a little bit? Because if you could shrink it so it's just slightly under the halfway mark, suddenly you can get twice as many parts per panel. So parts on the right are half the cost of the parts on the left, and all you did was shave off a few mils off the top end. So it's very important to look at how they're going to fit on your processing panel. And if you have vendors that you're currently working with, it's a good idea to know what their standard panel sizes are, so that when you're doing your design, you have an idea how it's going to work with their processing panels. Here's another example. If you had a flex that was just square, you can get 8 parts per panel. If you put this little extension off, you drop it by 25%. So you increase the cost of the entire board by 25% just for this little extension right here coming out the top and the bottoms of these squares. And you have to look at it and say, it would have been better to just use a single wire instead of having the flex come off like that. Another thing that is a huge cost driver is when a customer wants to get their parts in a pallet, if they're going to be doing additional assembly operations. And the pallet itself isn't a problem as long as you allow your manufacturer to work with you on finding out what the best pallet size is and the best layout of parts within the pallet. So here's an example of a poor use of space. You can see that there's a lot of just dead space. When I take these circuits out, everything else gets thrown in the garbage. And so I would say that probably 60 to 70% of my surface area is going in the scrap bin. But the customer is ultimately going to pay for that 70% of material that's going in the scrap bin. In this particular case, if the pallet was changed slightly, you can see how we've optimized the number of parts per panel that we're using, and that can have a huge impact on what the cost is, because we're throwing a lot less in the garbage and a lot less is going out to the customer. Another thing that is crazy is unreasonable X-out requirements. The number of X-outs on a panel is, what I would consider reasonable is typically 10 to 20%. A lot has to do with the size of the part. If you only have 2 parts per panel, 50% would be a reasonable X-out. But on smaller parts, you typically figure 15 to 20%. For most assembly houses, this isn't an issue because you can usually just X out a fiducial, and your pick and place equipment will just ignore the parts that have rejects on them. The issue is if you have an unreasonable X-out requirement, like no X-outs, and if you look at the previous slide that we just had, if I have to throw this entire pallet out because I have 1 reject on it, I'm going to have to basically assume that I'm going to be, there's going to be a number of pallets that are going to have that issue, and so I have to take the cost of a full sheet minus 1 part and amortize that into the parts that are being shipped. So it is going to have a market increase in cost if you have an unreasonable X-out requirement. So keep that in mind. If your assemblers are really struggling with that, you might want to look at a different assembly house because, like I said, it's not difficult to X out the fiducials and have the assembly equipment just ignore those parts and process the ones that are good on the panel.
Yeah, this is one of the topics that is, as something that should be considered, because as a flex supplier, when you also do assembly, we control the layout of the panel to maximize the panel. We don't have to worry about the X-out requirements. And typically, if there's an issue, it's maybe the EMS company or the CM aren't proficient at doing flex, or there's other reasons that they would come up with these types of requirements. But it is pretty important if you're going to maximize your cost. These are important things to take a look at.
Yeah, and flex is not easy to do assembly on. It's rigid boards are already, just by nature, they're flat and they're rigid and they hold up really well to your screen process and your the pick and place and everything else. Flex circuits are so flimsy, and it's very difficult to keep them flat for solder pasting, and they're dimensionally unstable, so they grow and shrink. There's a lot of issues with it, so it is more difficult to do assembly on flex. So when you're picking, an assembly house, make sure they have experience with it, because that's huge. Not all assembly houses do well with flex, and they can really struggle mightily if they haven't done it before. So make sure they have a good amount of experience if they're going to be your chosen assembly house. Another cost driver is a circuit type. By this I mean a pure flex versus a rigid flex. These are cross sections. A flex circuit is the upper left. It's just standard flex materials. A rigid flex is the lower right, and that basically has FR4 laminated top and bottom. Sometimes there's even FR4 cores. That's an expensive option. Usually isn't necessary. Usually it's just the outer layers. What it does is it gives you a very rigid area to put your SMT components, both top and bottom layers, because you'll have circuitry etched on those layers. And then you basically have the flex that runs to the other rigid areas, so you can basically eliminate connectors and just have rigid boards with jumpers already built in. But it is more expensive to do that, so a lot of times there's other ways to accomplish the same thing. So it's important to ask yourself a few questions when you're looking at which way to choose. This is an example of a rigid flex, where you can see you have your flex tail and then the rigid board in the green area there. And this is a very similar circuit, but this is just a pure flex. Now the difference is the previous one had SMT both sides. And I'm not showing the back side here. You can take my word for it that there is SMT in both top and bottom, and the rigid flex allows you to do that. This is just a standard flex, and a stiffener's been added to the back side. So you can put SMT on one side and put a mechanical stiffener on the other side, and this will save you a ton of money. This is probably less than half the cost of the other option. So if you only have a couple of components on one side and you're looking at a rigid flex, it's definitely worth spending the time to see if those components can be squeezed onto the top side, get all your surface mount on one side, and go with just a standard flex option. Another thing to keep in mind is if you have multiple areas with SMT, they don't all have to be on the same side, but each individual SMT area, it has to be on the same side. So like on this example right here, all the SMT in that one block is on one side. If on the other end I had a similar pattern, but the SMT was on the other side, that's fine. We can put the stiffeners on both sides, and you could have SMT on the other side on the other end. But in each individual area, it needs to be on one side, because as you can see, the stiffener will not allow SMT on the other side. Feature size, this is basically a yield driver. It's our processing equipment has gotten a lot better over the years, so we're able to get much better yields. But as things get smaller, and as we get better at what we do, everything just keeps on shrinking. And so, anytime you reduce the yields, that's going to have an impact on the cost of the circuit, because the rejects get amortized into the overall cost of what does get shipped. This is an example of small features. If you're using just your standard negatives to do your printing, let's say you print, let's say this is a 10 mil pad, and you print another layer, and then you have another layer, and you have another layer, and you have just a couple mils of misregistration, and now you have to drill a hole and try and get annual ring on all the different layers. That can be very difficult to do. A couple things will happen there. Either your yields will go down, or you're going to be forced to using laser direct imaging, which increases your cost because you'd have sequential lamination. So if you can give yourself an extra couple of mils on your pad sizes and your trace size, it can definitely help on the yields for your manufacturer, and that will result in cost savings. Material types. For our base laminates, we can get adhesive-based, where the copper is held onto the dielectrics with a thermal-setting adhesive. We can also get adhesive-less, which is a little bit more expensive. It's getting better, but those are better for higher temp applications because you don't have any thermal-setting adhesive. LCP, I typically try and steer people away from that because it is very difficult to use and it's expensive. And now with the other materials that give you the low loss features, you're better off going that way. And any other non-standard, I mean, every once in a while we'll get something and there'll be a material called on a drawing I've never seen before. It doesn't mean we can't do it, but you'll typically pay a premium if it's something that requires some front-end test work just to see if it can even be done. Your via hole types, through holes and blind vias are, through holes are the cheapest, followed by blind vias. If your blind vias are only going from an outer layer down one layer, those are fairly inexpensive because you just have one plating operation. When you start having buried vias or multiple layers of blind vias internally, that can drive up your cost quite a bit because now you'll have sequential laminations where you're basically going to start on your internal layers, do a drill, a plate, a print, develop, etch, put on another layer of copper top and bottom, and start the sequence over again. Each of those sequences, you're going to have additional yield fallout, and you're using very expensive equipment because you have to be able to target and laser drill based on where your targets are. So it does make the circuit a lot more expensive. Over-dimension drawings. It's important to keep in mind that flexible circuits are flexible. Don't dimension it like you have a machined piece of steel because it's not. They're very flimsy. They're just slightly thicker than Saran wrap, and they can grow and shrink just with temperature and humidity up to 1 mil per inch. And I've actually had applications where customers have called me and told me there's a fairly long circuit was out of tolerance because it was too long, and I'll tell them to throw it in a low bake oven for 15 minutes and remeasure it, and it shrinks right into tolerance. So it's important to remember it's a flexible circuit. It's flexible, and it's meant to have a little bit of slop in it. So always make sure that if you put a dimension on a drawing, make sure it's critical and something that really needs to be held tightly. Otherwise, all you're doing is paying for us to measure something that you don't really need, and that'll add cost to the circuit also. Dissimilar layer counts. What you want is any area that has a plated through hole structure, you're going to want to make sure that the layer count is the same in each of those layers. So if I've had applications where I've gotten designs in where a circuit looks kind of like a dog bone, and on one end it's 6 layers of circuitry, and on another layer it's 4 layers, and they're asking to remove the 2 layers thinking it's going to save money. And it's like, well, it'll definitely have an impact on the cost, but not the direction you want it to go. If you ever have that situation, you either need to figure a way to get the 1 6-layer down to 4 layers, or add 2 pad layers on the 4 layer to get up to 6 layers, because you want to have the same layer count in all layers that have plated through hole layers. It's a major pain. It can be done that way, but it's a real pain, and there will be a major premium. You could probably expect a 3 or 4x increase in cost if you have dissimilar layer counts in plated through hole areas. Excessive size. Anything over about 18 inches is starting to get into that area where you're going to see your supplier base start to drop off, just because equipment made for flex circuits, there's limitations on that, and you'll have yield issues. You'll find that U.S. manufacturers will go a little bit longer than the Asian manufacturers, but typically just figure if you're over 18 inches in length, it's probably going to start to get to be more expensive. Copper weights over 2 ounce. Most of our stuff is built in Asia, and I would say that 90% of it is half-ounce copper or less. The rest of it is 1-ounce copper. We rarely see 2 ounce or more. In the U.S., 2 ounce is not that uncommon. It doesn't mean you can't do it. It just means that it's going to be a little bit more expensive, because if it's a material you don't typically stock, you're not going to be buying the same volume of it, so you'll be paying a premium when you do get it for a particular job. Multiple finishes. By this I'm talking about the final finish at the very end. It's best to just pick one. If you're going to be doing SMT, your best bet is ENIG over the entire board. What you don't want is ENIG in one area and electrolytic gold in another area. It can be done, but it requires hand masking and 2 separate plating operations. So you're going to basically mask one area, plate the other area, then strip off the masking, mask the first area you plated, and do another plating operation. And those masking operations are typically done by hand with someone either putting down tape or a paint-on type of masking. And it's time-consuming, and it adds a lot of cost. So again, for your final finish, it's best to pick one and go with it. And that's the end of our presentation. So we're ready for any questions you might have.
All right, thank you for that great presentation. Okay, let's see what we have in the queue. Okay, here's our first question from the audience. What advantages are there to using a flex or rigid flex expert during the design process, and can they help me get to a cost-effective solution?
Well, yeah, I mean, most of the pitfalls that we covered during the presentation here, it's tough to beat experience. You know, if someone's been doing it for 10, 20, 30, or some of us 40 years, I usually tell my customers, I can't tell you everything that will work, but after 40 years, I've seen everything that won't work. And if I can steer you away from all the pitfalls, you know, you have a much better chance of success. And so it's you know, find someone that's done it before, that has some experience doing it, and let them guide you. And any reputable any reputable manufacturer is going to want to help guide you, because no one wants to build something for you that doesn't work. So yes, it is important to make sure that you have someone that knows what's going on when you're doing your design.
Excellent, great advice, and that was a great question. Okay, and on to the next question from the audience. What panel sizes are typical, and what is the usable area for those sizes?
If you are building in the United States, the most common panel sizes are 12 by 18, 12 by 24, and 18 by 24 for flex. And figure about 3/4 of an inch around the perimeter of that panel is non-usable. It'll be needed for tooling holes and things like that. I would say the most common is probably 12 by 24. A lot of that is driven by the 2 main manufacturers of material used in the United States. Their material is 2 feet by 3 feet, and that's the stock material that you get it in. And so a 2-foot by 3-foot panel would be just way too big for flex, and so those are usually cut down in half, which gives you 18 by 24, and quarters, which gives you 12 by 24. So, those are the most common sizes. In Asia, most of the material comes in rolls rather than sheets, and the rolls are 250 millimeters wide. And so you're looking at 250 millimeters in width, and then as far as length, you're probably looking at 300 to 450 millimeters in length. When at our factories, we actually have some proprietary processing equipment that allows us to vary our panel sizes anywhere from, in length anyway, anywhere from 250 up to almost 500 millimeters. So we can pick the most effective panel size, because what you don't want is extra panel that just gets thrown in the garbage because it doesn't fit. So by reducing the panel size to best fit the circuit size, we can save money. But like I said, you're typically looking in Asia about 250 by 300 to 450 is your kind of your range. And same thing, probably 3/4 of an inch around the perimeter of that panel also.
Excellent, thank you for that. Okay, and to the audience, we are in the Q&A session. We have a few more minutes. We're going to try to answer as many questions as we can. But if you do have a question or a comment, we would love to hear from you. You can add that to the Q&A box and click Submit. Okay, now for our next question from the audience. Do you have other recommendations for reducing costs for rigid flex boards, such as hot bar soldering a flex circuit to a rigid board or adding a connector to connect a rigid board to a flex board?
Yeah, there's a lot of ways that you can do that. And the drawback when you're doing that is you will have multiple components, but a lot of times those multiple components can be a lot cheaper, and it's definitely worth it, and it's worth looking at that. We have done hot bar soldering. When you do hot bar soldering, it kind of depends on, you will have to take special considerations on the flex portion of it because you will want to use an adhesiveless substrate. You're typically limited to just a single layer of flex going between your rigid sections. There are ZIF connectors, which are great. We see a lot of use of ZIF connectors. They're inexpensive and easy to use. If you open up your cell phone, you'll find a lot of them in there. That seems to be what rules the roost inside cell phones. So it's a very economical way of basically linking your rigid boards together without going to a true rigid flex. If you have multiple layers of flex, you may be stuck with a rigid flex. But again, have a conversation with your manufacturer, and they can pretty much steer you which the best option is.
Great, thank you for that. Okay, it looks like we have time for one last question, but I see two in the queue, and I'm going to combine them here. But Mark, I think you can handle it, and here it is. How tightly can I bend a flex circuit, and how do I terminate a flex circuit?
For the how tightly you can bend it, again, we're going to it goes to the bend ratio, your circuit thickness to bend radius. And for a single or double-sided flex, your single or double-sided flex, you're looking at a 10x thickness to bend ratio. So if you have a 10 mil thick circuit, 100 mils would be your minimum bend radius. If you have a multi-layer, you're looking at 20-to-1 for your bend ratio. And for termination, pretty much anything you can put on a rigid board, we could put on a flex. So, there's some things we will have to, stiffeners and other things we may have to incorporate into the flex to be able to do it, but we can pretty much put any kind of rigid PCB connector onto a flex. And there's additional options you have with flex that you don't have with rigid boards, like the ZIF connectors, for instance. So there's a lot of ways to terminate flex.
Excellent, thank you. And we do have one last question that we're going to try to slide in here before we close. I'm going to try to get this right. Mark, you may need to help me with this, but the question is, are there pad and size combinations?
Pad via size.
I think that's what the gentleman is asking. Q12 in the queue there.
It's just pad slash via size.
Yeah, pad via. For when you're looking at your via size and your pad size, the best rule of thumb is bigger is better. So the more, for the via size, I typically don't like to go under 4 mils. I mean, the industry has found that your reliability on vias under 4 mils is not good. There's a pretty sharp drop off there, and that's industry-wide. That's not just one manufacturer talking. That's across the board. Then you're going to want to make your pad as large as possible. The larger you make it, the better our yields are going to be. If you make a pad that's only, 4 thousandths larger than the via size is, we're going to pretty much be forced to using a laser direct imaging machine to do the imaging on it. So it's going to be more expensive to do that. So if you can give us 2 or 3 times that, it would be great. Again, that's something. It's probably a good conversation to have with your supplier, during your design stage, and to find out what you should be setting your parameters at when you start doing your layout. And you can talk to a couple of different manufacturers and get kind of a good mix. But most of them, I think, you're going to find are pretty standard based on how many layers you have and the individual feature sizes you're looking at using.
Great, thank you. And that was our last question, so we are going to wrap things up right there. So guys, thank you so much for that great presentation and also taking the time to answer some questions from the audience. Take care, and we'll talk with you soon.